Understanding Materials, Lecture 6 by Lee Burton. So far we have learned the basics of band diagrams. Now let's go deeper in interpreting them. We saw how once an electron is promoted, it is free to move through the conduction band. The state left behind is now empty, allowing neighboring electrons to fill it. This absence of an electron is called a hole, and has an effective positive charge. Just from being the absence of a negative charge, it isn't really a positively charged species in its own right. On a band diagram such as this, electrons prefer to settle down, whereas holes prefer to rise up. As an analogy, you can imagine electrons are water droplets in air and holes are bubbles underwater. The highest point of the full bands is called the valence band maximum, which is where holes typically float up to. The lowest point of the empty bands is called the conduction band minimum, which is where excited electrons typically settle down to. Next we can see the curvature of the band. Highly dispersive bands indicate strong bonding in the corresponding direction of the Brillouin zone. Remember that the paths in reciprocal space relate to direction frequencies in real space, whereas flat bands mean weak bonding. Bending is quantified as charge-effective mass. Flat bands lead to heavy mass and low mobility, and bendy bands lead to low mass and high mobility. The valence band maximum and conduction band minimum can have very different bendiness, leading to very different effective mass for holes and electrons. It can also be seen how many states there are. This is quantified as density of states, or DOS, by summing across the band structure at a given energy, and is often shown along the side of the band diagram. Notice that energies with many bands have peaks in the density of states, and the density of states decreases to zero at the band gap. Now we know everything we need to understand solar energy. First, we know the energy spectrum from the sun. Remember that wavelength is proportional to energy for photons. And we have a clear peak in photon flux. So we can pick a material that will absorb the most light. The optimal band gap for a solar material is 1.3 electron volts. And the band gap should be direct in nature. There should also be a high density of states around the gap, because more states mean more charges can be made across it. Conduction band minimum and the valence band maximum should also both be bendy. For low charge effective mass, which corresponds to high mobility. Again, all of this information can be seen on this one diagram, as long as we know what to look for. And now we do. No wonder physicists think band diagrams are so important. Understanding materials, end of lecture 6.